All right, this is section 9.3, which is going to continue with what we did in class, which is look at infinite series that goes to infinity, and determine if they converge or diverge by using a bunch of tests. So yesterday we learned the first three tests. Test 1 was called the telescoping test. Test 2 was the geometric series test, which is actually one of the most common ones. Test 3 was the nth term test for divergence, which is also pretty common but only shows divergence. So now we are moving on to test 4 and test 5. So test 4 is called the integral test. I have what the integral test actually says written on the screen. It's called the integral test because you actually will integrate. So what happens with the integral test is you are looking at a series that we can actually write it like it's an improper integral. So this is taking us back to a couple chapters ago when we looked at what do we do when an integral has an infinite boundary. So that's what we do. We're going to take this series and we're going to think of the formula for the series as being a function that we have to integrate. And we're going to integrate it from wherever it starts. Most of these start at 1 to infinity. So with these, here's how the integral test works. Essentially, what it tells us is whatever we get from the integral as far as converging or diverging, that's exactly what the series will do. So with improper integrals, if you got a finite number for your answer, we said that it was a converging improper integral. And if you got an infinite answer, then we said it was a diverging improper integral. So essentially, these will act the same. Now, we're going to only do this if it's a very easy to integrate function. It should be something you're very comfortable integrating, like U sub, something basic. It should also be something that we couldn't do an easier test. A lot of these, what ends up happening is if you think about like the nth term test for divergence, if we get a limit as we go to infinity of something that's not 0, we say it diverges. These are going to be ones that if you try to do the nth term test, you actually get a limit of 0, which means that the test won't apply. So those are some things to think about as far as when we start these. One other note is if you do an improper integral, and you get that it converges to a half, for example, that doesn't mean that the series converges to a half. We actually have absolutely no way of knowing what the sum of the series is with this test. We just can determine if it converges or diverges. So I'm going to take you through 3 practice ones, some ones that you see often. For these, what you're going to do is you're going to write it as a limit. Get my pen ready to go here. A limit as we go to infinity, and I'm always going to make the upper bound be from 1 to b, and then you're going to have x over x squared plus 1. So essentially, you're going to take this series formula, rewrite it in terms of x's, and take the limit as we go to infinity with this improper integral. So this is a very quick u sub. U is x squared plus 1, du is 2x. So we're going to divide both sides by 2. We get a 1/2 adjustment. This is a du over u, which is a natural log. So we get 1/2 the natural log of x squared plus 1, going from 1 to b. When you put your boundaries in, you get 1/2 the natural log of b squared plus 1 minus 1/2 the natural log of 1 squared plus 1, or natural log of 2. When I look at what happens as I take an infinite value and I take the natural log of it, so this first piece is the natural log of something getting bigger and bigger, natural log does get bigger and bigger. So this will go to infinity. It does not matter that we have a 1/2 natural log of 2. That will still be infinity. So we would say this one diverges by the integral test because we get an infinite value for the improper integral. Same idea for the second one. We're going to set up the improper integral the exact same way, going to infinity. These are all going to be ones that the upper boundary is going to be infinite. So we're going to say b is going to go to infinity. And we have 1 over x squared plus 1. This I will not be able to do a u sub because if I let u be the bottom, I have the derivative of x squared plus 1 is 2x, and I don't have an x in there. This is actually an arctangent with an a value of 1. So it is just the arctangent of x going from 1 to b. What you may or may not remember about arctangent is arctangent flattens out as we go to infinity. As you go to infinity, the arctangent flattens to pi over 2. We actually did a graph of this in class. The arctangent of 1 is pi over 4. Here's the thing. At this point, I really don't need to do more work. I know I'm going to get a finite number because I have no infinite values appearing. In fact, as soon as I realize it's arctangent, I know arctangent always gives me a converging improper integral. So I can stop right now and say that it converges by the integral test. And then this last one, natural log is a really common time whenever you would do an integral test because we can't do a lot of other things with natural log, to be honest. So we're going to go to infinity from 1 to b of the natural log of x over x. Anytime you are integrating with natural log, it has to be the u value. The derivative of natural log of x is 1 over x, which is exactly what we have. I have a 1 over x. This is just a power rule. Currently, this is just a u du because natural log is just being taken to the first power. So I get u squared over 2. So natural log of x squared over 2, going from 1 to b. And at this point, you may be able to stop because what you should realize is, again, you're taking the natural log of something that's getting bigger and bigger and going to infinity. That will go to infinity no matter what that lower boundary is. So this one also diverges by the integral test. Kind of writing sideways here so I can have my conclusion. The key with all of these, what we did in class and what we're doing here, is you should be able to look at a series, decide what test is appropriate, and then decide what that test tells us. Does it converge or diverge? That's how I'm going to set up quizzes, where you have essentially a form of saying, does it converge or diverge, and then what test tells us that information. One more test in today's lesson. This is the 5th one. There are 10 total tests in this chapter. We're going to do the first 5 and then take a quiz, and then the next 5 and take a quiz. Test number 5 is called the P-series test. The letter P actually stands for power, so you can think of it as like a power series test. This is going to be a series that can be written as 1 over n to a power, where that power is constant and it has to be a positive power of n. So it could be 1 over n squared, 1 over n to the half, 1 over n cubed, and the numerator can actually be any constant. So there is no limitation on this. We can use this test for any constant in the numerator as long as the denominator is n to a constant positive power. We do have a special case of this, that I mention it because I've seen this show up on the AP test. They will use this terminology, and I don't want it to throw you off. When you have just the series 1 over n, where your power is 1, this is referred to as the harmonic series, and a harmonic series always diverges. You can actually prove this with the integral test. Actually, this entire test, the P series, if you can't remember what happens with the power, every single one of these can be proven by doing the integral test. It just takes more time and more effort. So we kind of have a shortcut, which is to look at the power and determine what it does. So here are the guidelines. And it's all based on what that power is, what that p-value is. If you have a power that is bigger than 1, anything bigger than 1, it can be a whole number, it can be like n squared, or it can be a fraction, it can be a 3/2 power, it will converge. If you have any power that is between 0 and 1, including 1, we say it diverges. And again, we say including 1 because we know that 1 diverges because it is called the harmonic series. If you were to integrate 1 over x and write it as an improper integral, you would get a natural log, and the natural log as we go to infinity does diverge. So these are fast. There are very little work to do associated with this. It's more of an identification. So look, I'm going to take you through 3 really quick examples and then kind of mix up our 2 tests from today. So the first one, you'll notice your power is 4. Since it has a power of 4, 4 is bigger than 1, we would say it converges. And our reason is the P-series test. Next one has a power of 1/5. Because it's a 5th root, 1/5 is less than 1, so we say it diverges by P-series. Last one, I want to show you just that you don't have to have a 1 on top. You can have any constant on top, and the P-series still applies. This one, my P is 2, which is bigger than 1, so it says converges by P-series. I've even seen questions where they actually write out a few terms. So for example, I've seen ones where it is, see the best way to explain it, where you have something like 1 plus 1 over 2 root 2 plus 1 over 3 root 2, 3 root 3 plus 1 over 4 root 4. And you have to kind of establish what the form is and then use the P-series test. So what you have here is the denominator is always an n and a root n. So, because then again, you have like the first one will be 1 root 1, which is just 1. So you have 2 root 2, 3 root 3, 4 root 4. So what I have with this series, is I have a 1 over n to the 3 halves power, because it's to the first power and the half power. And when we multiply, we add powers together. So we would say this is a p series where p is 3 halves. So it converges because the power is bigger than 1. So that's a way to do it. Instead of writing it as a form, write it as terms where you have to identify what the pattern is and write the p series on your own. So some mixed examples just to make sure we don't forget what we just did. So with these, the first one, you could do a couple ways. We can integrate if you want to use the test that I just showed you earlier today. So you can set it up as the limit as b goes to infinity of 1 to b of e to the negative x. This is actually an improper integral we would have done back in chapter 8. So the integral of e to the negative x is negative e to the negative x, which may be easier to write as negative 1 over e to the x. Just move that negative exponent to the bottom. Put boundaries in, you get negative 1 over e to the b. Minus a minus would be plus 1 over e. As we go towards infinity, this is going to get bigger and bigger and bigger, which is going to make this entire thing go to 0. So we have 0 plus 1 over e. 1 over e is a finite number. So we can say that it does converge by integration, by doing the integral test. There's another way to do this one. So I just want to show you just in case you see this one and do it this way. You could actually write this as 1 over e to the nth power. That's what e to the negative n is. And you could actually do it as a geometric one, because you have now, with a geometric, we have a ratio, a base being taken to the nth power. This ratio is less than 1. When you take 1 divided by e is a number that's approximately like 2.71828. When I take 1 and divide by that, I get a ratio that is smaller than 1. So we can say that this converges by doing a geometric test. So you actually have two different ways, and that's going to happen. The more tests you learn, the more options you're going to have. The middle one is actually the one we just did, but we did it more of a term by term. This is a p series. Your p is 3 halves because you have the first power and the half power. When you multiply those bases, you get the 3 halves power. And that is bigger than 1, so this one converges by p series. You could also do this one by integrating. You could have integrated and used the negative exponent, and you would still get that it converges. Integration sometimes, especially if it's a very basic p series, it's way faster to do that than to go through the integration process, but it does give you a backup plan. This next one I am going to have to integrate just because we have some extra stuff. If it was just the square root of n, we would be good, but because it's the square root of n plus 1, we are going to have to write it as an improper integral. So we're going to take the limit as we go to infinity of, I'm going to write it as x plus 1 to the negative half. Make it easy to integrate. It's just going to be a really quick u sub. U is going to be x plus 1. The derivative is just 1, so there's no adjustment. So this is just going to be a u to the negative a half. So power 1 greater would be the positive a half. So we get 2u to the half. So 2x plus 1 to the half. Put your boundaries in. We get 2b plus 1 to the half minus 1 plus 1 to the half, or 2 to the half. When you put an infinite value in here, so when you take the limit at the end, when you take that infinite value and add 1 and square root it, it's still going to be infinite. So this piece is still going to give you an infinite value. Therefore, by the integral test, we say that it diverges. So to kind of summarize what we've done so far, and we will go through the summary again before we take the quiz. At this point, we now have 5 different tests for series. And so every question that you're asked as far as converge or diverge, you basically have 5 options to prove what you know. Your first test was called the telescoping one. Telescoping is not very common. This was the one where the terms started to cancel out, and basically you were left with whatever didn't cancel out. These do always converge to whatever you didn't cancel out. We have the geometric series. Geometric is incredibly common series. Geometric were the ones that had your ratio to the nth power. We also have like that a value. And the key is what that ratio number is. If that ratio number is less than 1, the absolute value of it is less than 1, then it converges. If it's bigger than 1, it diverges. We can also find the sum of a geometric series. Sum of a geometric series is your first term divided by 1 minus your ratio. And we'll review that, but that is something that shows up a lot on AP tests. And then we have the nth term test for divergence. The nth term test only shows divergence. And the idea is that if we get the limit of the series to be anything not 0, then we can say that it diverges, which makes sense because if my terms aren't getting smaller and smaller, when I add them together, I'm going to get something that will get bigger and bigger and will diverge. If you do get a 0 limit, which happens a lot, you can't use this test. You don't say, well, then it converges. It just means that this test is invalid. And then we have the 2 tests that we did today, the integral test, which you would really want to reserve for things that are pretty easy to integrate. Natural logs show up a lot in these. And then finally, your p-series, and your p-series are the ones that have your n to a power in the denominator, and the power will determine if it converges or diverges. Bigger than 1 will converge, 1 or less than 1 will diverge. If it actually equals 1, if it is just 1 over n, we call that the harmonic series, which is a special one that always diverges. So that's just a kind of a rundown summary on what we've got so far. We will recap these in class, and then we will take a quiz just on these 5 tests.